the top and bottom metal contacts. Then we learn a little bit about the p-n junction and some junction properties, and then we come to the conclusion that to really describe the realistic solar, you have to really use numerical methods. It's not simplistic formula to design this thing, So people have developed software for designing solar cell. Okay. So in order to go from the simplistic structure to a structure which can get high efficiency, what I'm going to do is to share you some results from that software, because that's the only way I can teach you a little bit what is really important in designing of the high efficiency solar cell. It's not like exact formula I can give you and you can just run that calculation. So that's why we're going to see some graphs, and then the homework will come for you is to generate those graphs yourself. Okay. So any question what we're trying to do? So we started with the losses, the optical losses and the electrical losses, and then we going through these calculations of the graphs to understand the various losses, how they affect, because that losses determine the optimum design of high efficiency solar cell. So last time we talked about the short circuit current is dependent on the diffusion length for different surface recombination velocity. So if you want to have a high efficiency, you need to have high short circuit current. To have a high short circuit current, you need to be working in a diffusion length at least 2 times the thickness of the wafer. Here in this calculation, the wafer is 200 micron thickness. Okay. So that's the wafer thickness. So you need to be at least 2 times in order to get high efficiency, and then your recombination velocity has to be low in order to get high efficiency. So that's what the simulation or modeling of the real solar cell is telling us. In order to design high efficiency solar cell, we must have diffusion length at least 2 times the thickness of the wafer and a low recombination velocity. Okay. Similarly, we learned about it also depends on the diffusion. And that shows you the dependence for various recombination velocity. And again, this one says be at least twice and higher recombination velocity. Of course, you could gain more by going to the having a diffusion length several times than the wafer thickness, but then the cost issue comes in. Okay. Now, let me introduce another concept, okay, is when you have a solar cell, and you put a metal contact here, okay, this is, okay, this metal semiconductor interface plays an important role. There is a lot of recombination can take place between semiconductor and metal interface. Okay, so we need to do something about this interface to lower the recombination loss. Okay, so that's where this concept of the back surface field comes in. Okay, so now we will learn what is back surface field. We learned that if you have a N-type material and a P-type, you form a P-N junction, right? Okay. Let me give you another case. Let's say you have N and N plus. Notice the difference. I don't have N and P. What is N and N plus means? What is N plus?
Different doping concentration.
That's right. That's right. N plus means higher than N concentration. Okay. So now you have a case, you have N and N plus, which you can do that because you dope it at certain level, and at the bottom you increase the doping level. Okay. This is similar to like a p-n junction also. Having that N plus, or you can have P and P plus even, So it's not just N and N plus, but having a concentration difference, because that causes the diffusion of the carriers, okay, and then develops the field, And similar to like N and P, you have electrons and holes, and they move around, create electric field at the junction. Here you have a difference in the concentrations, so they move around and create electric field. So by having this type of structure, okay, can overcome the problem of high recombination at this metal semiconductor interface. Okay. So that's why it's called back surface field, because you can make a layer here. You could have a P and then you have a P plus. So this is P plus and this is P. And now you have a interface, okay, and that will keep some of the carriers away and minimize the recombination, okay. But you still have to collect the carriers. So how do you go about that? You still have to make contact, okay, of the metal, So let me talk about this first, and then we'll address that part, okay? So this is from the simulation. This is the open circuit voltage. This is the back surface field depth, how deep that P and P plus layer, P plus layer is, okay. So that's the back surface field depth, for different surface concentration. Notice if you do not have the back surface field, okay, your VOC is only this much, okay. But if you have a back surface field, then your VOC will go up, okay. And VOC goes up means the efficiency will go up, okay. So you can see that by making a semiconductor with P and having a P plus layer, that allows to enhance the open circuit voltage. Why does the open circuit voltage goes up? What's the physical reason?
In total resistance, will reduce when
Okay, well the resistance certainly changed, but the where does the resistance is reflected in the efficiency? The efficiency is given by VOC, ISC, fill factor divided by the incident light power, So if you have resistance, which factor does it impact more? See, but more even the fill factor. Remember, that's the homework I gave you. Okay, shunt resistance, series resistance. Okay, so that affects the fill factor. So then the question comes is, why is the VOC is going up? Think about it. What did we do by putting a back surface
You
field?
reduce the recombination inside the device so more of those charge carriers can be separated to their contacts, so you get a larger voltage across the device?
Just a little bit louder. We just
So
could not
with the
hear
back
you.
surface field, you're lowering your internal recombination, which hurts your VOC because the more charges recombine inside the device, the fewer of them are getting collected at the anode and cathode.
That's correct. By putting a back surface, we decrease the recombination. Okay. And that decrease in recombination affects the VOC. Okay. So that's the reason why the VOC increases with the back surface field depth. Okay. Any other question? So now if you look at our structure, but we started with this structure, and from the simulations, we learned a couple of things. One, if you look at this, you have this, a base, and then you have, let's say this is P, and then you have N. So one of the things we learned, in order to get higher efficiency, the surface recombination has to be decreased. How do we decrease surface recombination? By passivating, right? So now we end up putting some kind of, let's say, dielectric layer, passivating it. Always struggle. Wow. Okay. So now the solar structure, which was here, now becomes a little more complex because we have to put a SiO2 and SiO layer in. Okay. Then, but we still have to make contact, right? In order to collect the carriers, we still have to make metal contacts. Okay. So we cannot put a metal contact on top of the dielectric. That won't collect anything. So we have to go deeper inside this dielectric and make the metal contact. Okay. But if you just put a metal on this N semiconductor, we just learned that that's not a good interface. That gives you higher recombination. So what we need to do? That's right. So what is done is we put a N plus layer here. Okay. Same thing, I had to make contact on the back, Right? But since it's a dielectric, it will not make contact. So I have to, etch away dielectric and move the metal here. Okay. But if I connect the metal here, then I have a metal to semiconductor interface, which will give me higher information. So how do I solve that problem? Make a P plus. Okay. So now I need to make a P plus. Okay. So now you can see that really the thing which we had a simple solar cell, simple a PN junction and a metal on the front and the back, now turn into this kind of design. But you need that if you want to get a higher efficiency. Okay. So now you see the rationale for why the solar cells are in this kind of design. If you are asked to explain the role of each layer in the solar cell, will you be able to do that? You should be, right? You should know what the role of the passivation layer is, what the role of the N plus layer, what the role of N layer is, okay? And similarly on the back side. Okay. One more thing I'm going to introduce you is we talked about the efficiency. That's the total efficiency of the sunlight with electric power. Okay. But for understanding what is going on in terms of losses and how to knowledge to build higher efficiency solar cell, we not only measure the total efficiency, but we also measure the spectral response of the solar cell, or called quantum efficiency. Means you measure that response as a function of the different wavelengths. Okay. So what is spectral response means really every photon coming out, electron it generates, okay, or collected. So if electrons are not collected, what happens to the spectral response? Below, right? Okay. So your goal is to have a high spectral response. Okay. And the other goal is to have a high spectral response throughout the solar spectrum, because that's what you will be detecting from sunlight, is you have different wavelengths. So your response should be high over a whole solar spectrum. Okay. So now it's that model results, okay, which assumes the junction is located half a micron, the surface concentration is 10 to the power 19, okay, and for different recombination velocity. So now you find out your response curve looks like this. There are 4 different curves. Okay. So if you look at this curve says while your response is close to the 100%, that's great, but only in a very narrow, wavelength range. If your response goes down in the blue part of the spectrum, and your response also goes down in the infrared part of the spectrum. Why is that? Why the response goes down in this part of the spectrum? Okay. So, what kind of recombination? Huh?
Like your front surface recombination?
Surface recombination, yeah. So this one, the surface recombination, because we know that surfaces add more recombination than the bulk, okay. Okay. So that's why, as the shorter the wavelength, it absorbs more towards the top surface and more the effect of the surface recombination. So that has the lowest spectral response. When the light is coming in the solar cell, okay, the blue light is absorbed in this one, the longer wavelength absorbed at different depths, okay. So those which are absorbed near the surface will see more effect, and that's why the spectral response goes down in the shorter wavelength part of the spectrum. Okay. And that's why you can see that when the surface recombination velocity is high, you see a lot more effect, But if you can improve the surface recombination velocity by passivation, okay, then it doesn't go down as fast, And if you can bring it to this level, then the spectral response is pretty flat. Okay. So for the solar cell, your goal is to have your high spectral response and flat response over the full solar spectrum. Any question? Why does this goes down now? That's not, you are still within the band gap, huh? The band gap will be somewhere here, Yeah. Why this goes down? How many surfaces you have?
The back surface.
That's right. Right? So this part is placed the front surface. And this part is the back surface. And this is more of a base, Okay. So you see that surfaces can cause this this efficiency to go down front and back. Okay. So having these kind of measurements is very important for understanding why the efficiency is low in the solar cell. Okay. If you measure the total efficiency, it doesn't tell you why is it low. But if you do this spectral measurement, you get to learn, this is going down, the surface recombination is playing a role, my passivation is not good. I need to improve my passivation. Okay. Okay, let's look at some few more design simulations. We looked the effect of ISC and VOC. What's the other parameter which really affects the Louder. Fill factor. Okay. What else? That's fixed. That's nature has given you sun. What happens if there is no light and you still get current? What do we call that? Dark current. Huh? Okay. So the dark current is also important because dark current can affect the VOC. Okay. So we looked at ISC and VOC. Now, a couple of slides, we will look at the dark current as a variable. How does the dark current changes with the design parameter? Okay. So here is a plot of the dark current as a function of the surface concentration for different recombination velocity. Okay. So a couple of things to notice, from this one. Or maybe let me ask you, what kind of surface concentration will you choose to get a higher efficiency? What kind of surface concentration will you like to have to get higher solar cell efficiency? That's not a hard question.
Lower than the value we normally do.
Lower what?
Yeah, about 10 to the 19.
Okay. So the goal is to have this low, right? Yeah. Okay. How do you get this low? You look at this thing. If you are around here, okay, then that's the lower. If your doping is in this region, 10 to the power 20, then the dark current is higher, Okay, so a couple of things to learn from the dark current, dependence on the concentration. One, you want to have your doping concentration around 10 to the power 19, Okay. Why not even bring it down more? Maybe make it 10 to the power 18. What's the problem? Once the surface recombination will be affected, what else? If your doping is low. That's right. Because it will be more resistive, right? It gives you the conductivity or lower resistance. So if you lower the too low, okay, then your resistivity will be higher, conductivity will be lower. And that will affect your fill factor and that will affect your efficiency. So again, there are always trade-offs. Okay. You have to be in a region to compromise one effect versus the other effect. So what we are learning is if you are given a homework, go make me a solar cell. Okay. I give you the access to the clean room, I give you the silicon wafer. Okay, and you are trained how to use the equipment. And now your job is to make a solar cell. What questions will you ask? Because you need to start somewhere, right? So what do you need in order to make a solar cell? So let me go around the class. I'd like to tell me what thing do you need so that you can go in the clean room and make a solar cell.
Can I make a proper doping?
Okay. So one of the questions you will ask is what kind of doping level I need, Well, doping of what? N or P? Right? So you need to know what? That's the question. What doping level I should use for N and P? Okay. That's one question. Okay. What other questions?
How can I make a perfect surface?
What does it mean, perfect surface?
And how can, for example, how to build a test layer?
Okay. So, well, but no, that's not a complete question. How can I build a passivation layer? You are given a task. Okay, as a scientist, you go in the lab, and you have equipment. So, what questions or what information do you need to make a solar cell, a high efficiency solar cell?
The thickness, depending on the diffusion that is there.
Thickness of what?
Of the wafer, of the layer, and for example, of the
Which layer?
end layer.
Okay. So that you need to know is the junction depth, right? Okay, so you need a doping level, you need a junction depth. What are the things you need to really go and think about, like you are going and making a solar cell? Your chance to ask me a question, otherwise you go and then you can't come back from the clean room. What do I do now?
Which material you're using?
Okay, for which part of that? Yeah.
Well, you can have different material for different P and different N type materials.
Well, we are making a silicon solar cell. So we take that silicon is our starting material. Okay, what other questions you need? There are many questions you're not asking.
Do you want a multi-junction cell?
What it is, you're making like a in contact, right? How you're gonna.
I have not gone beyond planar, right?
Okay.
So it's a planar. Yeah. But what we have learned, okay, let me ask you, Dilip. You need to make a passivation layer. What information do you need to make a passivation layer? Thickness, right? Well, what material I should use, how thick I need to use, okay? And then you also need to know is how I'm going to make that layer. Let's say you need to make, let's say we say SiO2 is a passivation layer. So I gave you the material and I gave you the thickness, okay? Let's say you need a 20 nanometer thickness. Without that, you don't know where to go. I mean, you need this critical information, okay? So point I'm making is what we are going through this thing allows us to get the information you need. You can go and fabricate a solar cell on high efficiency because this gives you the design space where you need to be to get higher efficiency. If you deviate from this design space, your efficiency will be lower. Okay? The other thing from this graph, again, you notice that the surface recombination velocity also has to be low. How do you get more surface recombination velocity? How do you get that? We have been talking about it, nobody asked that we need a low surface recombination velocity. But how do you get that? Okay, so passivation, okay, that's what controls this. So what it means, I need to know my time and temperature and thickness and material conditions, okay, which I have control, I can vary it, and certain conditions of processing or the interface will give me that lower. If I do not put, let's say I put this SiO2, which is porous or something, okay, then you're not going to get a good passivation, okay. So getting a good quality SiO2 is important to get it. And this is where people learn from experience sometimes, finding out the conditions which work. Okay? It's not that easy to calculate. Right? Another design space, the dark current as a function of the emitter penetration depth. Okay, how deep the emitter should be. What do you think you like to have emitter depth? As low as possible, right? Because this is where the dark current is lower, you know. So that's why in a p-n junction, okay, if you have p, the n is only, 100 to 400 nanometers, so it's very shallow. While this one could be 200 microns, Okay. The starting wafer could be thick, okay, but the N layer is typically, you can see, it's pretty thin, because thin is better to get that lower dark current. Okay, so this is what we talked about. In reality, the solar cell, you start, let's say, P-type wafer. Okay, and then you make your N junction, but where the metal goes, okay, under the metal you want higher concentration, and then you notice there is a SiO2 passivation layer here, and so what you do, you take your wafer, you make your junction, and then photoelectrically you dope certain regions with higher level of concentration. And then you open that SiO2 layer, and then deposit metal. So the metal is contacting not SiO2 but your N++ layer. Okay. So that is what typically people use sometimes for certain type of solar cells. There are half a dozen different design, configurations people have come up with making a high efficient solar. Each company comes with their own idea, Okay. But the basics are similar. You need some high doping level under metal to make a good contact, minimize low recombination loss. You need a passivation layer to minimize surface recombination loss. That basic is same, Okay. Similarly, you can see what's done in the back. You take and put a SiO2 layer, back surface passivation. Then you put a metal everywhere, but why don't you want to make metal contact everywhere? In this design, the metal is contacted only at certain selected points. Why is that? Because the metal semiconductor interface is a recombination site. So less the contact area you can get by, better you will be. So that's why they make these holes and make contact, and there is enough, carriers can be travel and get collected, So still they can travel and get collected, But that's where the design comes, how far this separation should be, And that's where their software simulation is run to find that, what is the spacing or what percentage of area metal should make contact. You have a choice of making 100% or you can make 5%. Okay. So what I have basically described you is the more realistic solar cell is your higher efficiency rather than what we started with the PN junction. But everyone in the class should know the role of each layer, why it is done, okay, and what it leads to. Okay. So that time, in the previous graph, we were looking at the surface concentration, Okay. What about the base, the wafer, What should be the starting wafer concentration we should choose? Okay. So this is a plot of the efficiency as a function of the dopant concentration for the base and for different cell thicknesses, 100, 200, and 400 micron wafer thicknesses, and assumes the surface recombination velocity is 1,000 centimeters per second. So what do you think your starting wafer should have the concentration? That's right. So somewhere around, depending on the thickness, this is where you want to be, right? So that's what the commercial solar cell do. They start with a wafer with about 10 to the power 16 to 10 to the power 17 concentration, Okay. Why not go higher? Why does the efficiency drops? Why is this shape? Why is it drop on here and drops here?
You go higher, you get trap space, and you get more liquid that you combine.
Yeah, that's right. If you go to the higher concentration, you will have a higher recombination in the base. Okay? Why not here? That's right. The resistivity will be high, Okay? So that's why you need to be in this region in order to get optimum value. So this summarizes what we've been discussing. This is the cell efficiency versus peak doping concentration. If your doping goes down, your resistance goes up. If your doping goes high up, your recombination goes up. Okay, and that's why people stay around in this region of the doping. Okay. Another simulation. This is the fill factor as a function of the dark current. Now, dark current is divided into two components. Anyone remembers?
Bulk start cream and the surface start cream.
It is, one is the base, okay, and other one is space charge region, So we have two, we call I01 and I02, So this is more of the base type, this is more of the combination in the space charge region. So this is plotted the fill factor as a function of I02, okay, dark current, due to the more recombination in the space charge region for various values of I0. Easy to do simulate, and you assume something vary and for different conditions. So couple of it shows you that. Okay, well maybe I should ask you, what is I02 value you like to achieve? What value of I01 and I02 you like to have to get higher efficiency? Just not
low
hard.
I2.
Huh? Low I01 and low I02, right? So you want I0 to be in this region, okay? And among this graph, you want high fill factor. So you want to have about this one, which gives you that you want I01 is about 10 to minus 11 type, I02 like 10 to minus 9 or 8 values, If you do that, then you will have a chance of getting high efficiency. And if you fabricate a solar cell and you find that your dark currents are very high, you know why your efficiency is low. Okay, so let's summarize what we have learned from the simulations. In order to achieve a high efficiency solar cell, we need to have the base dopant level around 10 to the power 16, right? So that's one thing. So when you go in the lab to fabricate a solar cell, you make sure you choose a wafer, silicon wafer with a doping level of that in the range. Okay. So that's the one design parameter, that the base doping should be around 10 to the power 16. That also reflects, if you have 10 to the power 16, how else can you say that? You can say that the resistivity of the wafer, right? Because the doping concentration affects the resistivity. So you could say that resistivity should be about, this translates into like 1 ohm centimeter, Okay. Means you want to have a wafer with that kind of resistivity, or means this much concentration. So that's we learn about this. The base should be 10 to the power 16. What about the end layer? How much we learned about that? That should be about 10 to the power 19. Okay. The end layer should be about 10 to the power 19 concentration. So you start the wafer with a 10 to the power 16. You dope it with N-type dopant to the 10 to the power 19 level. And that will be the right recipe for getting high efficiency solar cell. Okay. Then both surfaces needs to be passivated in such a way the surface recombination velocity is between 100 to 1000 centimeter per second. So now you need to passivate these surfaces with SiO2. So that's another thing we learned. Okay. Then we learned that the diffusion length, the quality of this wafer, not only the doping, but the crystalline quality and the impurity of this wafer should be such that the diffusion length is 2 to 3 times the wafer thickness. These are some of the we learned from our design graphs, we looked at it. Okay. The N layer, the emitter, that should be about 0.2 micron thickness. The vapor is about 200 micron, but this layer should be about 200 nanometer. That's based on the simulation. Other thing we learned that the recombination, the dark current, this is space charge recombination, should be 10 to the power minus 11 m per centimeter square. That's another design parameter about the I02. I01 should be about 10 minus 8 centimeter square, m per centimeter square. So these are the information you need to fabricate in a high efficiency solar cell. The shadowing by the finger electrode, the top electrode we put, that should not be blocking sunlight more than 2% of the area. Okay. Any question about what we have learned? We'll use a software to provide some insight into how to really design a efficient solar cell. And from the simulation, we'll come up with some design parameters. And those data parameters are discussed in this slide. Okay, so now comes the homework. Okay. So you will learn this. Let's make it. I think now they have 2D, program. So some of the graphs which are given in the book, okay. I want you to generate those graphs. So you understand that when I was discussing the design parameter, where they come from and how to really design a solar cell. This is in the textbook. Well, we only have one textbook. Okay. Yeah.
Are most of these just in the slides as well? Are most of these graphs also in the slides?
I'm sorry, what?
Most of the graphs from the textbook are also in the slides. Is that correct?
Yeah, that's right. That's right. Yeah. I just copied from here. Yeah. Okay, so Thursday we're going to start is looking